Hello all, welcome to this tutorial in which now we will be looking at some of the unfinished proofs or unfinished steps that was described in week 8 lectures. It will be a nice algebraic exercise and then let's do it. Now, there were actually three places in which a couple of things were, what do you call, just given as statements. Now, one is, now what is the sum of two normally distributed random variable? Okay, if x is a random variable and y is a random variable and z is x plus y, and what will be the mu and sigma of z? What is mu z and sigma z is the question. Now that has to be expressed in terms of mu x mu y and sigma x sigma y. How do you express it? That is the first point. The second one was, now you wanted to compute in the forward process. We wanted to compute this quantity q of xt minus 1 given xt comma x naught. We wanted to compute this quantity. Now this was left as an exercise. Now using the idea of completing squares. Now don't worry, I will also not be doing it. This is an algebra, even this is much more algebraic exercise. I'll point you to the reference from which you can go ahead with that. And the third one that we left is how do you compute the KL divergence between two normally distributed values. Okay. Now these are the three steps that we left, or we directly stated the results rather than going ahead and deriving the results. Okay. Now let's derive these results in today's tutorial. Okay. The first one that we want to look into is sum of two normally distributed random variable. So I actually mean they are independent. Okay. Now that is without saying. Now it goes that the random variables that are under consideration are actually independent. Now let's say that x is a normally distributed random variable. Now with mu x and sigma y square, mu and variance, and then you have y, which is a normally distributed, with mu y and sorry, this is sigma x, this is sigma y square. Okay. Now we want to know how does z look like. Now z is x plus y, and we know that intuitively it makes sense to us to say that z is normally distributed with mu x plus mu y, comma sigma x square plus sigma y square. Now, you can even simulate this and look at it. Now, since we already know how to generate random variables using a specific mean and then the deviation, now you can generate with some mean, okay, and some another mean. So, for example, let's say mu x, let's say it is 2, and mu y, let's say it is 3. And then sigma x and sigma y, let's keep it as 1. Okay, and plot the histogram and see how does it look like. And intuitively also you can understand, yes, this specific result makes sense. Okay, then programmatically we can do that. That is also a nice idea of doing it. Yeah, but we need to look into the mathematical proofs. Okay, so now what we shall be doing is, now in this case, we'll be using the idea of characteristic function. Now there is one more way in which we can prove this, which give rise to the idea of completing squares, which is algebraically, actually it is intensive and challenging. Not because it involves a lot of algebra. So it's like it has too many terms to look into, and keeping track needs uh, much more elaborate exercise. So I leave it as an exercise. Now you can look at it in Wikipedia. If you just type sum of normal distributed random variable, you get a Wikipedia page in which they have used convolutions to prove it. That is also one way possible. But I'll be doing the proof in this session using the characteristic function. Proof using the characteristic function. And I'm assuming that you're all aware of the idea of characteristic function. Okay, so now the characteristic function of z, now which is x plus y of t, as phi of x plus y, I'll write it explicitly, is equal to expectation of e to the power of I t of x plus y. Okay, so now the characteristic function, the characteristic function for a normally distributed random variable, okay, of normal distribution with mu as the mean and sigma square as a variance is given by phi of t equals exp of ITU minus sigma square t square by 2. This is what? This is a known formula. Okay. So now what is that we want? Now we want phi z of t. Now if we are able to bring the phi z of t into this specific thing, whatever is here will be the mu, and whatever is here will be the variance. Okay. Now that is what we want to do it actually. Now this is phi of x plus y of t. Now since x and y are independent, we can t into phi y of t. Now substituting this specific equation, now you will get exp of it mu x minus sigma square t square by 2 into exp of it mu y minus sigma, okay, this is sigma x square, this is sigma y square t square by 2. Now this is e to the power of something into e to the power of something. So now that is e to the power of this plus this. Okay. Now this is exp of it is common. Now this is mu x plus mu y. Now since you are adding it, minus, now if you take minus as common here and add these two terms, okay, now you have sigma x square plus sigma y square into t square by 2. Okay, yes, this is what the format in which we wanted. Now this means that, now this is the mean and this is the variance. Now this actually means that z is normally distributed with mean mu x plus mu y and sigma x plus sigma x square plus sigma y square. Okay, this is the formula. Okay, and then use this and substitute in the error computation that we did. Now, where is that? I can even show you the step in which we needed this. Somewhere above. Yes, here is what we needed here. Yes, here. This is a normal distribution. This is a normal distribution. And this is ax plus by. Okay. Now I just did for x plus y, and then I assume that from this you are capable of doing it for AX plus BY. Okay. So now if X is, okay, just give you the first part. If X is normally mu X and sigma X square, now what will be the distribution of AX? Now this is normal distribution A into mu X, comma, A square into sigma X square. I think from here you can extrapolate it, and then you will be able to obtain the result in this case. Okay, this is AX and BY. Now from here, now you will be able to extract it. Okay, so now since both of them are mean 0, now you get 0. So now your whole aim is to get the sigma. I leave it to you as a nice point. Okay, this is the first task that was partially finished. Now you have pointers on which you can extend it. The second one, which was the completing squares, you can look at the Wikipedia page that I referred to you. The third one that we wanted to look into is actually the KL divergence. KL divergence between two normally distributed random variables or two normal distributions. Okay. So now I'll say that I have P, which is your distribution, which is X. Now this is normal distribution mu1 and sigma 1 square. Now you cannot take X and Y here now, because whenever you are calculating KL divergence, the support for P and Q has to be seen. So you have to refer it as X only, otherwise notationally it doesn't make sense. This is also on the same space, n mu2 and sigma 2 square. Now you have to find the KL divergence between these two. Now how do you define KL? Now DKL between two distributions P and Q is given by, now P and Q is having densities P and Q, okay, small p and small q. Okay, now this is given by integral over the space of X, P of X, log of Px divided by Qx dx. And by now this formula should be by heart to you, and since we are looking at the normal distribution, here we have the support from minus infinity to infinity. Now minus infinity to infinity, you have this is a normal distribution X, now with mu1 and sigma 1 square log of normal distribution X, which is mu1 sigma 1 square divided by X, which is mu2 and sigma 2 square dx. And does it look like something we know? Yes. Now, this is nothing but expectation with respect to distribution P. Okay, with respect to P, log of, whenever we write log here, we always mean ln. Okay, normally we write log there. X mu1 sigma 1 square divided by normal X mu2 sigma 2 square. Now this is what we want to calculate now. Okay, so now let's do it. Now expectation with respect to P. So now we know this log of, you have two term. Now 1 over 2 pi square root of 2 pi sigma 1 exp of minus half into x minus mu1 by sigma 1 whole square. Now this is your numerator. Now divided by 1 over square root of 2 pi sigma 2 exp of minus half x minus mu2 divided by sigma 2, okay, whole square. Okay. This is full log. Okay. This whole thing. Log of this whole thing. Okay. Numerator and denominator. So now, okay, let's do this. Now this is there is an expectation with respect to distribution P. Then log of sigma 2 square divided by sigma 1 square, square root of this, exp of something divided by something. Okay, e to the power of something divided by something. So you know how to do it, right? You have to subtract. Okay, now this minus this. Now, since you already have a minus, that means that this plus this. Okay, so now this will be exp of minus half into x minus mu1 divided by sigma 1 whole square plus half into x minus mu2 divided by sigma 2 whole square. Now this is exp and this is for the log. Okay, so now next step is, I presume that it is pretty much clear what to do. This is log of sigma 1 square divided by sigma 2 square divided by sigma 1 square. Okay, since there's a square root, you write half here. Okay, and then exp and log will get cancelled. Now this is minus half x minus mu1 divided by sigma 1 whole square plus half x minus mu2 divided by sigma 2 whole square. All of them inside the expectation. Okay, so now you can immediately see that we should take half as common factor. This is in our notation, I'm using capital P. I should keep my notation consistent. Exp of half into, okay, so now what are the things that we have? Okay, this is minus of x minus mu1 divided by sigma 1 whole square plus x minus mu2 divided by sigma 2 whole square. Then this is minus log of sigma 1 square divided by sigma 2 square. Yeah, I think you can understand this. Now, log of a by b is minus log of b by a, right? That is the idea that I have utilized here. Okay, so now what you will do, let's expand these terms. Now we still have expectation with respect to p outside. Okay, you have half. Now you have this x minus mu1 divided by sigma 1 whole square. Now there is a minus for this, plus x square minus 2 mu 2x plus mu2 square divided by sigma 2 square minus log of sigma 1 square divided by sigma 2 square. Now directly understand why did I do this? Why did I not expand this term and I only expanded this term? It will be pretty much clear in the next step. So now you have an expectation here. Expectation of A plus B plus C is expectation of A plus expectation of B plus expectation of C. Now the expectation can be used as a linear operator. Okay, so now this, when I use it, okay, so now I can directly write it as, now this is half, I'll just keep as it is, this minus expectation of x minus mu1 whole square divided by sigma 1 square. Okay, sigma 1 square is independent of x, so I don't need to worry about it, plus expectation of, now this is x square minus 2 mu 2 into expectation of x, okay, plus mu 2 whole square divided by sigma 2 square, and this is a constant, so log of sigma 1 square by sigma 2 square will be as it is. So now, do we know this term expectation of x minus mu1? Now, this is expectation of x minus mu1 whole square. Now, this is nothing but the variance, right? Okay. Now, we know this actually. Now, what are the terms that we know here? We know that expectation of x minus mu1 whole square is nothing but variance of x actually. Now, what is variance of x in this case? It is sigma 1 square, right? Okay, now this we know already. And then, what are the next things that we know? And then this is sigma 1 square, this is sigma 1 square. Now you will get minus 1 out of this. Okay. Now what is expectation of x square? Okay. So now expectation of x square, I urge you to do it. This is mu 1 square plus sigma 1 square. Now this I can resubstitute. Okay. Now if I substitute all these things in our current thing, this is half minus sigma 1 square divided by sigma 1 square plus mu 1 square plus sigma 1 square minus 2 mu 1. What is expectation of x? No, this is mu 2 into mu 1 minus mu 2 square divided by sigma 2 square, correct? Minus log of sigma 1 square divided by sigma 2 square. Okay. So now we have this minus 1 which is there. Now we can rearrange the terms now. Now this is half mu 1 square minus 2 mu 1 mu 2 minus mu 2 square divided by sigma 2 square plus sigma 1 square divided by sigma 2 square. Now what did I just do? I rearranged this, and this. I took it as one term, and then this, and this, and here, putting it here, minus log of sigma 1 square divided by sigma 2 square minus 1. Now what is this? This is half. This is mu 1 minus mu 2 whole square divided by sigma 2 square plus sigma 1 square divided by sigma 2 square minus log of sigma 1 square, sigma 2 square minus 1. Okay. Now this is the equation. Okay, nice algebra. So you just no, what did you just do? Okay, no, the algebra is you feel like too much things. Now you just substituted these, rearrange the terms, took the log inside, took the expectation inside, and substituted the values. Okay, now this is what you have done. Now this you can see it in yeah here. Okay. How do you actually take? Now you can see here. Now you have the trace of this now, which is same as this term. I'll urge you to look into it later. Okay. D is there. Now in this case, which is one, this is one dimension. How does it convert? This which you have is same as this term, and this which is there is same as this. How is this? Now see, you see suddenly a trace is coming, suddenly an inverse is coming. Now why is this? And the idea is pretty much simple. See here you are dealing with x, which is in R actually. Your normal distribution that you're considering is a scalar. Now here, now you're considering actually a vector valued distribution. Now because of which you get sigma, which is a matrix actually. Now at that time the algebra becomes even more what do you call sophisticated. Okay. Now with this intuition that you have, now I urge you to extend the same idea into the vector valued random variables, which will be a nice algebraic exercise again. So now in that case, now you should be at each time, you should be looking at the equivalent of the vector valued substitution for the steps that we have carried out. Okay. Now with this, we will end this tutorial. I think this tutorial was algebraically nice, and then all the substitutions that we do are simple algebraic manipulation just by looking at the symbols. Now I want you not to get scared off. Okay. With this, we will conclude this tutorial. Now let's meet in the next tutorials, in which we code the DDPM model. Okay. Thank you.